Assalamualaikum warahmatullahi wabarakatuh. Um, I welcome you all guys to EK373 um, Advanced Power Electronics, and for today's session we're going to look on the three-phase AC controller. Um, Three-phase bidirectional controller are normally used in AC motor drive. We have a three-phase supply, and this is connected to the three-phase AC motor drive. Here example in the circuits, the three-phase supply are connected to the resistive load that are balanced. The firing sequence of the thyristor is T1, T2, T3, T4, T5 and T6. At any time, there can be 3 thyristors on, 2 thyristors on, or no thyristor on at all. So previously we learned about the 3 types of AC controller. The first one is the on-off control AC controller. The second type is the half wave and full wave single phase AC controller, and the last type is the cyclone converter. So the three-phase AC controller is the extension of the single phase AC controller, where you have now a three-phase AC controller that we're going to control the AC input and convert to the AC output, that is to drive a much bigger load. So the way we look at this circuit is imagine that the three-phase AC controller, the working principle is like the single-phase full-wave AC controller. So for the three-phase is like combination of 3 single-phase full-wave AC controller, but the difference is that for each of the supply phase they are 120 degree each apart, like say between the VBN and VAN and VCN VPN, they are 120 degree apart. So it's like a combination of 3 single phase AC controller. How do you going to look on the output wave? Okay. The first scenario, if when the firing angle is 0, or the thyristor itself is the firing is 0, or the thyristor, we replace it with a diode. So when the firing angle is 0, the thyristor function as normal diode. So we look at this circuit. So the input will be identical to the output when we use diode or the firing angle is 0. There is no change. All the input power goes through the output power. As the firing angle increasing, we saw a decrease in the output of the load magnitude voltage in the output. And since this is a balanced resistive load, so the thyristor will turn off whenever the current becoming 0. So if when we want to examine how the output voltage look like, we examine the output as one of the loads in the three-phase output load. because this load is identical, it's just 120 degree up phase between each other. The shape will be symmetrical. But for the purpose of starting with examining this one, VAN. Okay. You see in this side, in the circuit, VAN is equal to this VAN, is the phase voltage. Line to line voltage between A and B is combination between VAN and VBN. As I mentioned earlier, that to see what's the output voltage in VAN phase, we're going to determine by how many thyristors are conducting at that instantaneous time. At any time, there can be 3 thyristors, 2 thyristors, or no thyristor at all. In the case of 3 thyristor is on, this will correspond to balanced 3-phase source connected to balanced 3-phase load. The voltage connected to each phase of the load corresponding to line to neutral voltage. So, if 3 thyristor is on, example T1, T6 and T2, the voltage between phase VN is exactly the VAN. I repeat, if 3 thyristor is on, the voltage between VAN is exactly VAN here. For the second case, if 2 thyristor is on, example T1 and T6, so here when T1 T6 on, the phase load voltage is equal to line voltage divided by 2. Okay, line voltage is between A and B. This is the line voltage, and because the load resistance VAN, VBN are symmetrical, so the voltage VAN are identical to VBN and is a half of voltage A and B, the line voltage. So I repeat, when 2 thyristor is on, the voltage VAN here is half of the line to line voltage of A and B. And the third scenario, when there's no thyristor is on, the output voltage is 0. And please note that the thyristor will be turned off when current equals 0 or when the voltage becomes negative. Now we're going to examine the phase voltage in this VAN. We're going to look in more detail. So here, this is the case of 2 thyristor on. When 2 thyristor on, you can see the voltage is a line to line voltage divided by 2. So the output waveform will follow this waveform. Again, if another 2 thyristor on, depending on which thyristor that trigger, if 2 thyristor on, this will follow the line to line voltage divided by 2. And if 3 thyristor on, this will follow the phase voltage VAN. Okay, this is the phase voltage VAN. So how do you know how many thyristor is on, how many thyristor is on? You have to look on the table. table that show the triggering sequence of the thyristor. Then you know which to plot the graph. I'll show you in the later stage. So this is condition where no thyristor is on, so the output magnetic voltage is 0. This is the reading material for you to read, understand, and okay. In this example, we look on the firing angle when alpha is 30 degrees. Okay. At start, when alpha equal to 30 degrees, I think I'm going to pause here. Okay, now we're going to look an example on when the firing angle is 30 degree. How you going to plot it? Okay. First of all, before you plot, you should know what is the sequence of the thyristor that on. So to check the sequence here, this is thyristor 1 on firing angle during 30 degree. But previously, before the thyristor 1 trigger, we can see there are thyristor 5 is still on and thyristor 6 is still on. So when we trigger thyristor 1, at this instant we can see that S5 is still on at this point 30 degree and S6 is still on, so it's 3 thyristor on. So as we move along to 60 degree at this condition, so we can see that thyristor S5 already turned off and only thyristor S6 is on, so only 2 thyristor is on. And for the next 30 degrees, thyristor 1 is on and thyristor 6 is on. And then as we move here at this point, thyristor 1 is on and we have thyristor 2 conducting and thyristor 6 still conducting, so 3 thyristor is on. So this is the triggering switch sequence. So this is to tell you how many thyristor is on at that particular instances, so that you're able to plot according to the phase line to line voltage or the phase voltage. So in the case of here, when alpha is 30 degrees is firing, so this is condition there are 3 thyristor is on, as thyristor 1, thyristor 5 and thyristor number 6. So when the 3 thyristor is on, this will follow this curve. This curve is the phase voltage or VAN. So from this point to instantaneous 60 degree, at this point 3 thyristor on. So at this instantaneous point, before moving 60 degree to 90 degrees, the thyristor S5 is off, so currently only thyristor S1 and S6 on, so there are 2 thyristor on. You see, as I explained to you that Whenever two thyristor on, this is follow to line voltage, and this is follow this curve. So at this point only two thyristor on, so the graph will follow this curve, 90 to 60 degree. So at 90 degree, the trigger interval here to here, there are three thyristor is on, so you follow the phase voltage, this one, and up to this 120 degrees there are only two thyristor on, so you follow the line to line of VAC, and up to this point three also thyristor is on, so we also go to the phase voltage, and once it's reached 280, all the thyristor that conduct positive is 0, and we have 0 voltage, and the process continue. Okay, so this is the VAN that we plot. So there are some slight words depending on the number of thyristor on off. So it's follow the phase voltage, half line to line voltage, phase voltage, half line to line voltage. So this is the shape look like. This is for the VAN, and then for VBN is identical except is 120 degree apart, and VCN is also identical but is 120 degree apart each later. So as you increase the firing angle, you can see the magnitude of the output voltage delivered to the load are becoming lesser and lesser. So this is example for firing angle to 70 degrees. For the case of 75 degrees, there's only two thyristors on, and alpha being 60 degree. So the shape will follow this line to line voltage divided by 2, and this is entirely two thyristor on, but at 135 degree, here there's a change in the direction of which thyristor trigger, so we follow the line to line of EC divided by 2. Okay, and then this is no thyristor on, and for the negative part is repeating the same. So whenever you want to plot the chart, you must know the sequence of the thyristor and how many thyristor on at that particular interval of time. So this allows you to plot the output voltage instantly. And then the last example, this is when the firing angle is very big, 120 degree. You can see when the alpha is very bigger, there's only two thyristor can be turned on at one time. But one thing to note here is the magnitude of output voltage are becoming less and less. So you increase the firing angle, the magnitude becoming lesser and lesser. This allows you to control how much power you want to deliver to your load, and this is very simplified. Okay, this is the text you can read and try to understand. And also, yeah, this is the case I mentioned. For alpha between 0 and less than 60 degrees, at any time there can be 3 thyristor on or 2 thyristor on. Okay, you can read on your own time. The second condition for between alpha 60 degree and 90 degree, and this is point only 2 thyristor can be on at a time. So the output voltage will follow half of the line to line voltage. And alpha 90 degrees also only 2 thyristor can be conducted at any point, any time. And when alpha bigger than 3, there's no time interval, so the output voltage is become 0. So you can read the text and understand. And and try to understand on go on. Yeah, by the way, if you have any question, you can come and contact me. Now we move on to the analysis. We define the input AC voltage, the VN, VBN, VCN, as equal to Vs sin omega t, while VBN is 120 degree lagging and VCN 120 degree VBN. The instantaneous input line voltage VAB square 6 V plus sin omega t plus over 6 and VVT square 6 Vs sin omega t pi minus pi over 2. VCA is square 6 Vs sin omega t pi over 6. Okay. Okay, I already explained the condition. Here, if you examine this graph properly, you note the number of the firing sequence 5, 6, 5, 6, 6, 1, 6, 2. This one, when alpha is bigger than 60 degree, so the number of thyristor on is only 2. It's only 2. And the case, so alpha 120 degree, so the number of thyristor on also 2, but there are intervals when there's no thyristor is on. So this interval make the output become 0. So when you want to plot it, you see this information is very valuable to know which sequence of the thyristor that turn on, to allow you to know whether you are plotting for the phase voltage or half line to line voltage. Now the formula. The RMS output voltage for delta connected load for alpha between 0 and less than 60 degree, VRMS is square root 6 Vs 1 over 5 pi over 6 minus alpha over 4 plus into alpha over 8 and roots. The RMS output voltage for delta connected load for 60 degree, alpha and 90 degrees. So is square root 6 Vs 1 over 5 pi over 12 sin 2 pi plus 3 square root 3 plus 2 alpha over 16 over half. And the last case, in between 90 and 150 degrees, the RMS voltage recap is by this formula. Note here, the RMS output voltage becoming less as the firing angle increases. Here is the normalized output voltage. If the firing angle is 0, then we got the output voltage is similar to the input voltage. So depending on the firing angle, we get how much the normalized output voltage. Firing angle 0, we got 0 output voltage. So the firing angle will determine what's the value of the output voltage. Now I have the exercise for you. A 3-phase 3-wire bidirectional controller supply a star connected load of R equal to 5 ohm and the line-to-line input voltage is 210 volt RMS 50 Hz. The firing angle is alpha pi over 2. Determine the RMS output phase voltage, input power factor. And this one, the load are balanced, meaning that each load got 5 ohm and is resistive load. So yeah, try to calculate and I will show you the answers. So I want you to pause the video and for 10 minutes do the calculation and try, and if you done that, then let's check the answer. Hopefully you guys doesn't have problem finding the exercise, and now let's check the answers. So for the solution, the line voltage is 200 volt and the phase voltage is 121.24 volts. So we're using the equation of alpha for alpha pi over 3. This equation is this square root multiply 1 to 1.26 alpha, and you got the RMS voltage is 101.94 volt. The RMS phase current is divided by the load here 5 ohm, and the output power is Pi square R 3I square R, because we have 3 phase. Since I load connected star, the phase current equal to the line current. Phase current is equal to the line current IL line. The input volt ampere 3Es minus supply line 3 minus 1 to 1.4 is supply, and the I line is a VA. The power factor is the output power divided by input power, so we got about 0.84 is lagging. Okay, that's all for the class now, and see you guys later. Thank you.